This conference will now be recorded.
Good morning and welcome to the Invasive Mussel Collaborative webinar, using boater data to inform risk models. This is Ceci Weibert with the Great Lakes Commission, and on behalf of the Invasive Mussel Collaborative, thank you for participating in today's webinar. The Invasive Mussel Collaborative was convened in 2015 to identify opportunities to advance scientifically sound technology for management and control of invasive dry-seated mussels to produce measurable ecological and economic benefits. If you would like to know more about the Invasive Mussel Collaborative, we encourage you to visit our website at www.invasivemusselcollaborative.net. Today's webinar is part of an ongoing series hosted by the Collaborative. The purpose of these webinars is to facilitate learning and information sharing on topics of common interest within the invasive mussel community. It will be recorded and archived along with past and future webinars on our website. While we always strive to minimize technological issues during these webinars, we apologize in advance for any issues that may arise. Further, I'd like to cover a few logistical items before we get to the presentations. Audio for this webinar is automatically streamed through your computer speakers once you join the GoToMeeting event. You also have the option to dial into the webinar using a telephone. To change your audio to a phone line, select the settings icon in the top right-hand corner of the webinar screen and click the phone tab. A call-in number will be displayed, as well as the access code and audio PIN. Once you are connected from your phone, click the red Turn Off Computer Audio button to reduce interference. In order to minimize the potential for interruptions and background noise, we have automatically muted all attendees. Attendees will remain muted throughout the webinar. Additionally, we ask that all attendees and presenters turn off their video cameras by clicking the camera button next to the microphone mute button at the bottom of your webinar screen. This will help to mitigate any bandwidth issues and reduce lag during the presentations. We do encourage and will accept written questions from attendees throughout the webinar. If you have a question, you may type it into the chat box, signified by the chat bubble in the top right-hand corner of the webinar screen. If you are experiencing technical difficulties, please send a message through the chat box as well. Questions may be submitted at any time during the webinar. Depending on time, we may answer one or two questions following each presentation, but the majority of questions will be addressed after all the presentations have been given. We will do our best to take all questions or comments during the webinar. If you need to leave the webinar before you have gotten to your question, we encourage you to review the webinar recording that will be posted on our website to hear your question and answer. Additionally, once the presenter is sharing their screen, a banner with sizing, screenshot, and zoom features will pop up to the right of the shared screen. You may increase the size of the shared screen by either selecting the Detach Cameras button that will open the screen in its own window, or by using the zoom buttons. Our first presenters this morning are John Marino and Kathy McGlynn. John Marino is a GIS applications developer with the New York Natural Heritage Program's IMAP Invasives project. His primary focus is the creation and management of standardized GIS-centric invasive species field data collection tools in collaboration with statewide partners. Kathy McGlynn is the Aquatic Invasive Species Coordinator for the New York State Department of Environmental Conservation. She is responsible for coordinating the implementation of the statewide AIS management plan. Kathy serves on both the Northeast Aquatic Nuisance Species Panel and the Great Lakes Aquatic Nuisance Species Panel, and is part of the Long Island Metro AIS Task Force and the New York State Hydrilla Task Force. She is currently Vice President of the Northeast Aquatic Plant Management Society. And with that, John, take it away.
Okay, so this is Kathy. So Kathy will be giving the first part of the section. I'm talking about myself in third person here, but good morning, everyone. So I will be providing a background for the Watercraft Inspection Steward Program app, and John will provide the deep dive into the data. So let's go to the next slide, please. Thank you. New York State's newest version of its AIS management plan was released in July 15th of 2015, and the goal of the plan is prevention, so to stop the introduction and spread of aquatic invasive species into and within New York State waters. Next slide, please. And seeing that we're on the Mussel Collaborative, we'll focus on some data from zebra mussels and quagga mussels. So in New York, zebra mussels have been found in the Great Lakes, Mohawk River, Hudson River, Lake Champlain, and Lake George, and they are still moving to inland areas. Next slide, please. Quagga mussels are a more recent invader to New York, and they are making their way into inland water bodies as well, and they are outcompeting zebra mussels and also living in areas of deeper, colder water than zebra mussels. Next slide, please. So knowing that these infestations occur in very large water bodies like the Great Lakes, Mohawk River, Hudson River, Lake Champlain, and Lake George, we know that the only control method we have for dealing with these sorts of species is containment. Next slide, please. Okay. So our containment efforts focus on both voluntary and mandatory efforts. So going quickly through the mandatory efforts, we have an amendment to our Article 3 of the NAV law, which requires protect your water signage at public boat launches. We also have the requirement to clean, drain, and dry all watercraft and associated equipment when arriving and leaving parks and DEC boat launches. Next slide, please. And most recently, we passed the reasonable precautions to prevent spread of AIS, Part 576, which requires all folks who use public waters, which I refer to as anything but your bathtub or pool, all folks who use those public waters are required to clean, drain, and dry or treat their watercraft and equipment. Next slide, please. So, knowing the background of our mandatory efforts to prevent the spread of AIS and contain particular microscopic AIS in various water bodies, it seems pretty natural to see that the top priority for the AIS management plan is the expansion of the watercraft inspection steward programs, which we have been working on since 2015. And the main goal for that program is to help people learn to do clean, drain, and dry. And also, we also know that that's extremely important for us because boats and trailers are one of the major vectors for transport of AIS among water bodies. Next slide, please. So I'm pleased to say, just as an update, that more than 96% of the boaters who have been offered services of inspection and assistance with clean, drain, and dry by our boat stewards have accepted that offer. And our goal is to have boaters be in the habit of clean, drain, and drying no matter where they go, and even if there's no steward present. So in an effort to track our progress and adaptively manage our program, DEC Parks and Natural Heritage Program developed a standardized digital survey called the Watercraft Inspection Steward Program app, which has many standardized fields and questions that then contribute to a centralized database. So next slide, please. Okay, so in 2020, we expanded our coverage to more than 200 locations. We've had more than 340,000 inspections. That does not include all public interactions, which is well over 400,000. And we had over 19,000 interceptions of invasives. 2 of those interceptions were hydrilla at Lake George and Lake Ontario. Next slide, please. As far as interceptions for mussels, we had a little bit less than 3,000 for zebra mussels and a little bit less than 100 for quagga mussels. Next slide, please. Here are some additional resources regarding additional information for the Watercraft Inspection Steward Program app, as well as the Watercraft Inspection Steward Program. And next slide, please. And now on with the show. I'm handing off to John to discuss the data. Thank you.
Okay, perfect. Thank you, Kathy. So on the data side, I will start with a distribution of launch locations utilizing the WISPA tool for 2020. We can see we had excellent usage of partner organizations across the state, ranging from Western New York and Great Lakes to Finger Lakes, into the Adirondacks and Lake Champlain, and then down into the Hudson and Delaware rivers, and even 2 locations on Long Island. And so not every site had full coverage for the entire season, but at least each of these locations at least had some coverage. So what type of data is collected through WISPA? Really, the primary fields are when the inspection occurred, the location, the direction, whether launching or retrieving, the type of watercraft, and did the watercraft operator agree to an inspection? If so, were any species or debris detected? As well as certain locations track information about watercraft decontamination as well. Now, this is just a subset. There are, as Kathy mentioned, many fields. Some are customizable by organization. So the way the survey works is that we use Survey 123 as the product. This requires internet to set up the tablets, and then once the boat launch stewards collect the data out in the field, come back into the internet connectivity, then they upload those records. And that data is then sent to ArcGIS Online, where it is viewable in a dashboard as well as in editor maps that we have for organizations. So this is just a graphic of what that looks like. Data comes in from Survey 123 into ArcGIS Online. From there, the program coordinators can view statewide data to get a sense of what's happening across the state, as well as be able to edit their own data right in an editor map that provides the ability to update any species, misidentifications, and so on. So a few quick results I'll just briefly highlight. We have had, as Kathy mentioned, almost 350,000 records collected, which is really pretty remarkable. We are seeing approximately 1 in 10 watercraft with any attached organisms. So that could be native species, invasive species, or even attached debris. That's just sort of an indicator of clean, drain, and dry. So, the boat launch stewards are looking for any, attached organic matter. And as Kathy mentioned, around 20,000 of those organism detections are actually invasive species. And looking briefly at watercraft type, so the vast majority of the watercraft inspected were motorboats or some type of motorized watercraft. Primarily motorboats, but personal watercraft also comprising a large share. Kayaks, though, and other non-motorized watercraft also comprise a significant share of the watercraft inspected by boat launch stewards. A quick note on some of the species detected. You'll see primarily plants are being detected most frequently. And even, number 1 being native water celery. So again, just reiterating that, boat launch stewards are looking for any type of organic material, any type of organism as an indicator of clean, drain, and dry for the watercraft. And thinking about connectivity, we see just over half of watercraft launching into a water body had actually been in that same water body in the past 2 weeks. And about 18% had been in a different water body in the past 2 weeks. And of those, if you see in the table on the right, the majority of those are from a different water body in the state. But certainly, even with COVID and everything, there's still several thousand watercraft entering from out of state as well. And we have more detailed, breakdown of these of this data, as I'll show in the next few slides. But certainly, this sort of gets at some of that connectivity. And so on the analysis side, I'll just briefly mention 3 analyses that we conduct statewide. and provide to the program, the participating programs. And what else is great about the program is that organizations also conduct their own analyses and then share those with others. So and provide that sort of local insight and knowledge. So it's a really excellent collaborative environment. So I'll first just start with our more summary statistics. We provide a fairly straightforward overview of each program's data, the data that was collected, essentially through charts and graphs that provide a view of the data fields that were collected by all of the boat launch stewards in that organization. And we provide this midway and at the end of each boat launch steward season. Next are spider diagrams, and here we're looking at where the boater reported that watercraft being in the past 2 weeks, if they provide that information, sort of as I mentioned earlier. So this, for example, this map is a view of connectivity to Saratoga Lake for last season, actually. So this, I believe, is for 2019. And essentially, it shows sort of a visualization of that connectivity, between water bodies as vector for its spread of aquatic invasive species. And so, as we have more of this information, we can create more of these, really interesting maps that show sort of statewide connectivity between various water bodies. And so we can look at, different water bodies across the state. And the final one I'll touch on is the what we describe as lead in need of observations. And this is an opportunity for us to actually join data from IMAP Invasives, the statewide invasive species database, to the WSPA data. And the goal here is to highlight areas in which particular aquatic invasive species may be undersurveyed for specific water bodies. And it does that by identifying those water bodies which have watercraft exiting the water with attached aquatic invasive species that are not known in that water body. So what does that sort of look like? This is a map of confirmed observations for zebra mussel in the state, sort of as Kathy showed earlier. And that's represented by the green points. And in orange, it's difficult to see here, but this is water bodies identified as having no known observations of zebra mussel, but that do have, again, these WSPA records of boats retrieving from the water with zebra mussel attached. So just as a brief example, Long Lake here in the Adirondacks, we see, we have in this map on the left, we have no green points, representing known confirmed observations for zebra mussel. However, this blue triangle here, highlighted blue triangle on the right, is representing a WSPA retrieving record, which has had some type of plant matter we can see over here on the right. And attached to that, we see that what appears to be a zebra mussel. And so the boat launch steward entered this data as identifying zebra mussel on this watercraft exiting. And so thus this water body now fits our criteria of being flagged for having no known population of zebra mussel, and yet there's a watercraft exiting the water with zebra mussel. So certainly we're not saying that this water body is has a population of zebra mussel, but we're able to potentially have stewards remain vigilant for zebra mussel and or potentially be a water body for early detection surveys for zebra mussel. So certainly we know there's some limitations with this analysis currently, primarily that it does not fully account for environmental characteristics of the water body. However, we believe it's a start to really identifying these higher risk vectors for particular aquatic invasive species spread, as well as potentially highlighting early detection survey opportunities. So I believe, interest of time, that is it for us. Hopefully this is a great background on the program and data for the WISP program. And we're certainly looking forward to the next presentations and using this type of data to help inform these AIS risk modeling efforts. So thank you so much, everyone. And at this point, I think I will turn it back over to Ceci.
Yeah, thank you, John and Kathy. All right, our next presenters are Jeremy Farrell, Sandra Nierswicki-Bauer, and Mark Frischer. Dr. Jeremy Farrell is a lecturer in the Department of Biological Sciences at Rensselaer Polytechnic Institute. He received his PhD from Rensselaer Polytechnic Institute in 2013 in biology, exploring biological recovery from acid deposition in the Adirondack Mountains. Dr. Farrell's work focuses on computational environmental biology with an emphasis on limnology and invasive species. Dr. Sandra Nierswicki-Bauer is a professor of biology and the current associate director of the Darren Freshwater Institute Field Station on Lake George at Rensselaer Polytechnic Institute after serving as the director for over 20 years. She received a PhD in microbiology from the University of New Hampshire and was a postdoctoral fellow at the University of Chicago. A former department chair of biology and interim dean of the Rensselaer Polytechnic Institute School of Science, Dr. Nierswicki-Bauer's work focuses on molecular studies of microbial and pico-eukaryote communities in lakes and rivers, invasive species such as zebra mussels and Asian clams, and water resource management and environmental remote sensing. And Dr. Mark Frischer is a professor of marine sciences at the University of Georgia's Skidaway Institute of Oceanography. He received his PhD from the University of South Florida in 1994 in marine sciences, specializing in marine microbiology, and completed a postdoctoral fellowship at Rensselaer Polytechnic Institute, where his work with invasive species began. Professor Frischer's research centers on the development and application of molecular biology tools in marine and aquatic ecology, including molecular approaches for tracking, detecting, and quantifying invertebrate larvae, including those belonging to invasive species. And with that, I think, Jeremy, you guys are good to go.
Thanks, Cece, for the introductions and opportunity to present our research on the development of ARMOR, which stands for Advanced Response Model for Organism Removal. I'll provide a brief introduction, then Jeremy will talk about the data collection, analysis, and model development. Finally, Mark will discuss how to move the use of the model to a useful tool for managers and others. So in the simplest terms, the overall goal of this project is to improve the efficiency and efficacy of boat wash station programs using a machine learning approach. Basically, we've hypothesized that identifying boats of high risk at potential points of entry, that is at the boat inspection stations, will improve the efficiency and efficacy of detecting and then mitigating invasive species introductions. I think we all know why we care. Invasive species have tremendous ecological and economic impacts, and we want to use the resources, limited resources we have, to prevent the spread of invasive species as effectively as possible. As such, we decided in this program to focus on movement of invasive species on trailered boats because this represents both a critical point of entry as well as an important point of contact for the invasives. The primary vector or transport mechanism for introducing invasive species from one water body to another, of course, is boats. And in New York State alone, because of wash stations inspections, there are up to 7,682 surveys that can be conducted in an individual day. Also, at a single location, in this particular case, Lake George, the $1 Million Beach here, up to 15,000 surveys have been taken at this one site alone in a single year. As with any approach, boat wash stations have advantages and disadvantages. The advantages include that the boat wash stations are effective. They provide additional information valuable for education and outreach, although some potential drawbacks are the time involved with the boat wash stations and the cost. So basically, to minimize potential drawbacks and maximize the advantages, ARMOR aims to facilitate or improve basically on-the-ground, real-time decisions to maximize the efficacy and efficiency of boat wash stations. Now, my colleagues Jeremy and Mark will explain how.
Okay, thank you, Sandra, and thank you, Steffi. As John and Kathy really eloquently put, they've put all these boat wash stations across New York State, and they're effectively surveying each individual who is either entering or exiting each lake. And from those surveys, we hope to take that data and make some good predictions based on the data there. So they effectively ask a series of questions. One question, which they always know the answer to, is what is the location of the boat wash station that they're currently at. Then they also have the date and time. And then they ask 4 basic questions that are useful for our model. One is, has the boat been in the water in the last 2 weeks? That's a yes or no binary question. Second is, what is the last water body this boater was in with this boat? Where was it last? And this will turn out to be probably the most important question for our modeling purposes. Additionally, they ask if they're entering or exiting the lake, or other water body, could be a river as well. And then what type of boat is being washed. And all of this data will be fed into our modeling effort. So essentially, what I said on the last slide was they asked what was the previous lake where they were previously in with that boat. And so that would be our previous water body on the right here. On the left is each individual launch in the lake gets its own, in the state gets its own data set. And from that information, we do some calculations. One, at each location, we know the latitude and longitude. So that's numerical data that can be fed into a model. 2 is we know how many boats were washed at that launch site. So we'll use that as a kind of a sorting mechanism in the model that we're going to build. Along with that, we also know how many boats have arrived from a previous water body. For instance, if a boat has come from one particular lake, we know how many times that boat has arrived from a different lake. And then we can also, because we have a lot of data now, 350,000 boat surveys this year alone. I'm very impressed with that. We now have a good indication of where invasives are coming from. And so we can calculate how many boats have arrived. We can calculate how many boats have arrived with an invasive species, and we can give it like a threat level, so to speak. What % of the time does a boat from this previous lake come with an organism or an invasive species? And then matching these 2 data points, we can measure the amount of distance the boat has traveled. That's as the bird flies if it was flying in a straight direction, not necessarily as the boat drives. Okay, so from this, you really need to just take away that we have both a launch. At each launch site, we're calculating these threats, and from each previous water body, we're calculating these threats. And from these threats, now we'll feed that information into the model so that we can make good predictions based on the information in the surveys. So in a sense, what we're doing is we're just taking a decision tree approach, but doing it a lot of times over and over again. So what we're going to do is we're going to build a machine learning model to make a prediction on whether or not each boat that arrives has an invasive species or not. The machine learning approach we're using is going to be a random forest classification, and that is a series of decision trees that are taking the data and splitting it and making predictions based on each individual variable in smaller bags. We could spend a lot of time on this slide, but really we need to just think about how we accomplish this. For initial model development, we need to take 70% of the data out of the to build the model itself, and then test that data with the 30% that remains in there. And because invasive species don't often arrive, thankfully, at our lakes, we oversample the frequency of the instances with invasive species on the trailer boat. Okay, and the amount we oversample those instances will be useful for when we get to when Mark Fisher talks about our risk management. So this is what you should expect from our next couple of slides. This is the output of the models. This is our confusion matrix here on the left. We predict in this box here that there is no invasive species. In actuality, there was no invasive species, so we correctly did not wash any boat that winds up in this box here. Whereas when there is an invasive species, when we predict that there is an invasive species, but there actually is not, we washed it when we should not have. Moving down, if we predict that there is an invasive species, and there actually is an invasive species, we wind up with a correctly removed invasive species. And then our worst case scenario is when our model predicts that there is no invasive species on this trailer boat, but in fact there is an invasive species present. And this is when the model breaks down and doesn't work correctly. Additionally, with this approach, we can sort of play a game with the data where we drop each one of these variables individually and see how the model is impacted. Does it get better or worse? And so when it gets worse, we know that it's relatively important to keep that particular variable in the model. And so we'll have a relative importance. The higher the value, the greater importance it is to the model. Okay, so with that as our backdrop, our initial development occurred on Lake George. The Lake George Park Commission established a mandatory boat wash stations in 2014. We, in 2018, said, hey, we've got a lot of data here, and we started this process of modeling each of these boat arrivals. Each boat arrival and departure is surveyed, and so we take that data and model it up to do this prediction. Okay, so our ARMA model is going to take that information and that survey information and build its model. And so for 2014 through 2017, we took 70% of the data and built the model and then trained it and then tested it on the remaining 30% of the data. And as you can see here, we predicted a no and actually had no 19,500 times, whereas we had predicted a yes and didn't have it quite right 12,000 times for an error in this direction of about 38%. We correctly predicted 126 of the arriving invasive species. However, we missed 6, and so that 6 is 4.5% of the actual data. So what was important to our model? Well, it was mostly the previous water body. If you look at these P's, that's our previous water bodies and the distance, those are the most important parts of our model, as in we need to know where the boat is coming from to predict whether or not it has an invasive species. No big surprise here, but now we have that information to say this is important to collect. Additionally, the specific launch location turned out to be pretty important for these models as well. There's 6 or 7 of them around Lake George. Even within this small amount of boat wash stations, we have need to divide the data based on that. Okay, so when we apply this to the 2018 data, we had built that data from 2014 through 2017, and then applied it to 2018 data. We wound up getting roughly very similar responses in our errors, 36% and 5% of the data, 36% of predicting our data. And Mark will talk in depth about what that 36% means. And so we'll just move on. So we'll take this Lake George approach and then move on to the great work that the New York State DEC is conducting with their statewide boat washing stations. Here in red is our Lake George, but they've gone across the state and have hundreds of these boat wash stations, and they're collecting really good data. And now even Lake George is part of this particular modeling. So what happens when we take this same approach to New York State data? Well, we get a reasonable model. We have a 56% error on the nose, not actually having an invasive species, and only 2% in having an invasive species. Small issue here is that for this model, it turns out the launch site is the most important part of the model. And this is because we're not getting as many of the previous water bodies present in the data set, and Mark will talk more about this. And so now I'll turn it over to Dr. Fisher.
Thank you, Jeremy and Sandra and the organizers for inviting us again. So continuing on what Jeremy has been talking about and Sandra introduced, trying to bring this model into an actual use, bring it onto the ground so that it can help us in these programs. It's a huge effort, as you can all, I'm sure you all are aware, probably being involved with them yourself. So the model itself, and no models are ever perfect, but they are sort of tunable. We can adjust them relative to what we want them to do or what our level of risk tolerance is. And that's all about balancing how much risk we're willing to accept, to be tolerant of, versus how much benefit we want. In this case, it's how much time we might save or how much less hassle we subject boaters to waiting in lines at boat wash stations. And I should mention this picture, this background slide, that is $1 Million Beach at Lake George, one of the most, I think it is the most busy launch sites in New York State. So without additional data, we can do a lot with the model to make adjustments about that and provide information to managers and say, well, use this model if we have this risk tolerance, or that if you want this kind of benefit. And the way that works really primarily is what Jeremy referred to as in his training process of how he's oversampling the positive. It's very much like a political poll, and we're all familiar, unfortunately, with those these days, that you can get kind of what you want based on what sample size you are and then how you analyze it. So you can build these models and you can say, we're willing to tolerate this much risk for that much benefit, and we can mess around with that. The more conservative that we are with respect to how much risk we're tolerant of, the less benefit we'll get. Next slide, please. So again, just to reiterate, refamiliarize with one of the confusion matrices that Jeremy showed, and just the captions there are change it a little bit different in terms of the error rate. So when we have that error, that 6% error, that's boats that we inspected unnecessarily. They didn't have invasive species, but we predicted that they might, so we washed them anyway, so that was an additional effort. The 5%, of course, is what we really don't want, and that is what we missed. Okay, next slide. And so the question really is that 5% acceptable? Next slide, sorry. So this is the kind of thing that we can play around with in these models, and this is an experiment, an in silico experiment that Jeremy ran with this model. He ran 12 different models, which the same model, but he parameterized them differently, ran them each 1,000 times, and you can see next slide. If you advance, yeah. We can adjust the risk and see what kind of benefit we get. So on the y-axis of that graph is how much increased risk there would be of introducing an invasive from the origin low to high. On the x-axis is how much savings we get. So if we were to be fairly conservative and say we're only willing to tolerate an increase of risk of 2%, in this case, these models say that we should get about a 32% savings in how many boat inspections we do. Next slide. If we're a little less risk aversive and we said we're willing to tolerate 5%, we can increase our benefit up to 62%. So this is in addition to how we build the model and the data that goes into it, we can also adjust the models and tune it to these kind of questions about how much risk, what our balance of risk benefits we would want. Next slide. And this, I would argue, is really a central role of management here in terms of applying and using these models, is to integrate all this kind of data, and particularly to define what our risk tolerance is. So, of course, management is getting guidance and direction from policies, rules, and regulations. Management, the research community serves to inform management, and in fact, the way this model came about is that the New York State DEC funded this project to build these kind of models. And of course, especially in a project like this, the public input is really important. They're the ones on the front lines waiting in those boat launch lines, using their precious vacation hours before they can enter into the lake or exit. So the management, I just want to say, has a really important central harmonizing role to play, and that's why we're so excited and grateful to be talking to you today. Next slide. So this relative importance that Jeremy was talking about, and this is from the Lake George data, what really showed up was that where the boats are coming from is really some of the most important data, and as he also alluded to, some of that data is missing in the larger data set. And it's harder data to get, admittedly, and a lot of times it's just not being asked or it's not being answered by the boaters. Next slide. And this is a specific role, I think, now that we have explored this model, built and exploring this model, and understanding that this is really important data to get. There's a real good reason to ask these questions. This is something that we should work on, and we hope we will work on to get better information. So there's always, Einstein used to say that the hallmark of good research is that it leads to more questions than answers, and that's certainly the case here. There's more work to do in terms of developing and exploring that model. Lots to learn by those in silico experiments. Of course, these models are going to get smarter and better as we continue to collect and improve the data. And I'm really excited about the next talk. We're going to hear about some network analysis, because that might help us build better models. Right now we have a lake-specific model construction that just Lake George and the whole state of New York model, but it probably makes more sense that based on the connectivity between lakes and regions, that those will probably be better models. So developing the network analysis and integrating into how we build these models will probably be important. And then lots of exciting work moving forward to implement the use of armor, and that's to continue to work with the DEC and the WISPA program to develop implementation plans. Of course, we're going to need we know we're going to need some training to go along with this, especially for the stewards that are on the ground. And I can't stress as much how important it is to get out the message about what we're doing, get input from the public about why we're doing these boat washes, how we're making them better, how we're taking into concern at people's time and efforts. And with that, I'll stop there.
Thank you. I will remind folks as we move into our last presentation that if you have questions or any other comments for any of our presenters, please enter those in the chat box, and we will move on to our question and answer session following our final presentation. So our final presenter is Nick Phelps. Dr. Nick Phelps is the director of the Minnesota Aquatic Invasive Species Research Center and an assistant professor in the Department of Fisheries, Wildlife, and Conservation Biology at the University of Minnesota. Dr. Phelps's research program addresses emerging threats to aquatic ecosystems and fisheries at the intersection of animals, humans, and the environment. Specific areas of interest include risk-based management, pathogen discovery and diagnostic development, and the application of epidemiological approaches to environmental problems. And with that, Nick, it's all yours.
All right, thank you, Stacy. Just to be sure you can hear me okay?
Yes, you are loud and clear.
Awesome. And thank you to the other presenters. Very interesting talks, and I got distracted listening to you and not thinking about mine coming up. Those are really interesting, and I suspect we'll have follow-up conversations after this. A lot of overlap here. Let's see. All right, so I want to first begin by acknowledging the team that's helped put this together. This has been a big long-term project. A few of these names will be familiar to the invasive species crowd, but many of them come from the veterinary and public health epidemiology world. We've really lent a hand on taking big, complicated data sets and trying to play around with them in sort of a network way. So I only have one slide here as a background, and the previous talks did a good job of explaining why we should care about this problem, why data-driven approaches are important moving forward, because it is an incredibly complicated world out there for invasive species management. And for better or worse, we've got a lot of infested lakes and a lot of data to play around with. Just to give you an example here, relevant to this conversation here in Minnesota, we have about 800,000 boats moving around about 10,000 different lakes, hundreds of which are infested with various invasive species. So we've got a pretty complicated situation and needed data to drive decision making forward. So we were asked about 6 years ago to start to develop tools, with our ultimate goal being to develop models that will inform risk-based management activities to prevent the spread of AIS. Now, this has been, like I said, a big project, and I only have about 20 minutes total to go through it all, so I'm going to fly pretty quick. I expect I'm going to leave details out that you're curious for. We can save that for the Q&A or follow up with me via email afterwards. So I'm going to jump right into sort of the outline here and the data that we're using to create models, how we created them, and how ultimately we create an online dashboard to visualize outcomes for managers to use. So the first data source that's relevant, and this list is going to look very similar to the previous talk. We needed to know where the invasive species were on the landscape. So for our purposes, we used the Minnesota Department of Natural Resources list of infested waters. Those are confirmed locations of various invasive species. We update the models weekly. We keep an eye on this and download the list and update the model on a weekly basis to account for new infestations, which really changes the dynamics in risk on the landscape. I could give an entire talk just on the water connectivity networks too, but we're going to focus on boats here. So I'll just summarize by saying we incorporated GIS layers of water connectivity. We verified with satellite imagery to create a really big, robust network of lake connectivity through rivers and streams, because this is, of course, another pathway for these invasive species to move. Spending more time now on the boater network that we've created. We relied on the Minnesota Department of Natural Resources Watercraft Inspection Program data set. This is a very advanced watercraft inspection program. It's been around for quite a few years, really improving over time in both the quantity of data that's collected and the quality of the data. It's an electronic format now, which makes it very easy for us to play around with. From 2014 to 17, we pulled that data set. And ultimately, I'll explain why some things were cut out, but in the end, we were able to use about 1.3 million inspection surveys. Like we heard about for New York, there was a lot of questions that were asked. Two that were most relevant to us were where were the boats before and where are they going next? And of course, we knew where they were at the time of the inspection. So for the previous lake visited, we had about just over 1 million connections. And we had just under 1 million connections of where they plan to go next. So pretty big data set to play around with now. Some of the challenges, and I won't dwell on this, but just wanted to let you know that there were challenges with it. The lake and county pairs, like locating a previous and future lake, they're independent choices in the survey instrument, and that created some challenges for matching a specific site for the network. About 20% of the survey data we had to exclude because the boaters didn't want to answer or they didn't know where the boat was before or going next. We are concerned about the potential issues of accuracy of this type of survey. It's recall bias, future activity might not ever happen, and it's possible that somebody just makes it up. But when you have this large of a data set, I think the main trends are being captured. And 1% of our boater movements were coming to or from out of state locations, and in the survey tool, we don't know exactly where those are coming from specifically, just out of state, so they're excluded. So we have, when we remove some of the duplicate inspections, if a boat was inspected when entering and exiting a ramp, we ended up with over 1.6 million movements. That happened at 737 different lakes represented here in green. You can have boats coming and going from the green lakes. They were connected to about 1,400 other lakes that were not inspected themselves, but were connected to the network, and about 7,000 that were not included at all. So we had a lot of questions and missing data. And we spent a couple of years working through this process of how to fill it in. And I don't have time to dwell on this point now, but I want to summarize how we filled up, the steps we took to fill these gaps in. We were able to, based on the known data, those 1.6 million known movements and attributes of various lakes, we used the machine learning algorithm as well and predicted the popularity of any given lake, where it was connected to, and then the number of boats that would move across those connections. We used training sets and testing data sets, just like you heard about for the New York approach. The modeling approach was slightly different, but the same concept. And ultimately, the true predictive power of the network, based on the validation with known data, was just over 97% accurate. So then what we're able to do is we have this estimated boat network of quote and unquote inspected lakes. So now we have an estimated connection of all lakes to all other lakes. And visually, you get the sense here at this map that Minnesota's got a lot of lakes and a lot of boats moving a lot of places. If we look at just the most connected, the top 10 most connected lakes, so an in degree, out degree measurement of a network or the highest centrality, you can see that there's a lot of connections. The top 16 lakes represented here are about 8.5% of total boat movements, but they're connected to over 80% of the lakes in the network. So few lakes are highly connected. That's the main takeaway. A couple other takeaways from the descriptive network statistics here, that infested lakes are much more likely to be connected to other lakes. Infested lakes, boats that leave infested lakes are more than half the time going to an uninfested lake. So there's just a lot of risk and things we could look at when you dive into the network statistics. The last data source is focusing more on subsetting that estimated network. just on the at-risk boats. So these are boats that move from an infested lake to an uninfested lake. And this will become really important for the watercraft inspection part that I'll talk about in a minute. So consider you have a lake that has zebra mussels and a lake that doesn't. That's a risky movement. If boats are moving between uninfested lakes, that's not a risky movement. And if you're trying to prioritize effort, this is a way to do it. So I move quickly through the data, and I'm going to move probably even quicker through creating the models here. We had two objectives. We wanted to develop a model to inform risk-based surveillance. Where can invasive species show up, and how managers might prioritize things across the landscape. And we also wanted to look at prioritization for watercraft inspection sites. Two very different approaches here, but also two very important questions. I'll begin with the introduction risk for surveillance. So here we looked at the main data sets that we had were the infested waters, the water connectivity, and the boat movement. There's additional data that we had from the watercraft inspection surveys and various things that we pulled into this, but those are the primary sources of information. We used a Bayesian modeling approach to basically build a model that would forecast the future invasion of both zebra mussels and starry stonewort. For zebra mussels, we took the first half. We built these back in 2018. They've since been updated, but for the purpose of these slides, half of the invasion history was up until 2012. So half of the invaded lakes had occurred before then, and half of them occurred between 2012 and 2018. So we built the model up to 2012 with known data. Then we simulated what would happen, validated it based on what occurred over that period of time, compared to actual events, and then calibrated it going forward. We predicted over 10,000 simulations over an 8-year period, what would the future look like. And we allowed the model, this was a 1-year annual time step, and every year newly invaded lakes would then become sources for future invasions. So this model learned on itself as it went forward. This is what the outputs look like. Two plots here. You can see the black bars are the predicted outputs from the model. And this is during that verification period. You can see the predicted outcome. The red circles are what actually happened. So you can see the model was predicting very well. Going forward, you can see what the model predicts will happen in the future. You'll notice, and we're talking about zebra mussels here with this crowd, but when we have a very little runway like we did with starry stonewort, the uncertainty is huge. And as these models continue to learn from itself and we get more and more data going into it, our predictive power just keeps getting better and better. So the model for prioritizing watercraft inspections, here we focused just on those at-risk boats, excluding all the other less risky trips. This is an optimization approach with our problem formulation to be selecting lakes for inspection stations to maximize the number of risky boats that are inspected. So really intercepting the boats from infested lakes to uninfested lakes. And we let the model, we allowed the model to put the inspection station at either the receiving or beginning site at uninfested or infested locations. We used GAM-CPLEX to solve the problem using integer programming modeling approach. The output for this, you can see we worked with several counties to ground truth this, see how they would respond to this type of idea. Really what you get is a ranking of various lakes within a data set and the proportion of risky boats that you're inspecting across the bottom. So if you have up to 10 inspection stations in this case, you could start to prioritize it in this way and estimate that you'll have about a 60% coverage of risky boats. So these models were helpful. We were working with managers along the way. But sitting on Excel spreadsheets and running expensive and complicated softwares was not realistic for them. So we put these online. Over the last year and a half, we've been building this dashboard called the AIS Explorer. We've got the URL here. I suspect it'll crash if you all go to it right now, but I'll have it again listed at the end of the presentation. So I'm going to walk you through briefly a couple screenshots of how this looks. So this is the home screen. You can click Start. It goes to this first tab, looking at the introduction risk for surveillance. This is the same model that I showed you, just an updated version of it, now visualized online for the public and managers to use. So this will show you every lake in the state, the % probability that it will become invaded within 8 years. We can do this for both zebra mussels and starry stonewort. You'll see on the left-hand side a few options for people to play around with, different layers they can do. They can also export this as a CSV file if managers, for example, wanted to look at a ranked list of invasion concern. We can click on any individual lake. You can get some of the demographics about it. You'll see here Long Lake in Candiota County. Incoming boater traffic is estimated to be about 25% of the boats coming to that lake. So a fairly high risk, over a 50% chance that in 8 years that lake is going to become invaded. You can see one of these spider web figures here, like you saw in the last presentation. Click on any lake and see where the boats are going to or coming from. And it's hard to see at this scale, but the lines are weighted based on the proportion of boats that are going across that connection. So thinking about the watercraft inspection portion now, again, the same model that I talked about before, but now visualized and user-friendly for managers. This one, you'll see on the left-hand side, this is done at the county level. County managers can customize the lakes that they want to include or exclude from consideration for locating an inspection site. And there could be a number of reasons we heard from county managers of why they might want to do that. Importantly, this does not remove the data or the connections between those lakes. It just removes it from being a potential site for inspection. They can also pick the species that they're concerned about. We added 4 here to start things off. And they can set their management objective. How many of those, what proportion of risky boats do they want to inspect? Here for this example in Aiken County, if they want to inspect 60% of the risky boats, this model suggests that they should allocate resources for 17 inspection sites at the lakes that are prioritized here as they scroll down. And it provides a plot of diminishing returns if they are to add more inspection sites. You can see this, they can visualize it on a map too if they want to look that way. So if we were to add in this Aiken County example, not just zebra mussels, but if they want to worry about all 4 invasive species and keep the same management threshold, they need to inspect 19 different lakes. So adding 2 more sites. And if we change that management threshold, let's say to 80%, they now need to inspect 52 different locations within their county. Just again, giving them a tool for prioritization, and they can export all of this as images or tables as they see fit. So I flew through that very quickly. I apologize for the brevity and the methods in particular, but there are a lot of directions where this can go. We've got ongoing work to add complexity with existing data. There's much more to our inspection data that the DNR provides on boat demographics. We incorporate a time component. If an inspection manager wants to allocate effort for a time of day or day of week, we could add that complexity in the future. I'm also looking at seasonal patterns for risk. We could incorporate multi-county cooperation for watercraft inspections. We've run different scenarios of counties working together, and we see very significant trade-offs for counties thinking about themselves and prioritizing in-county risk versus working with their neighboring counties together, very different outcomes. And efficiencies, I think, can be found when you work together. And we could add additional species, of course. We've done a fair bit of environmental suitability modeling, and for a while we had it incorporated into the model, but we have not included it in the online dashboard because we heard from managers that they were more worried about the introduction risk and would not inspect a lake because a mathematical model said it was at low suitability. So we're really focused, what I've shown you, on the introduction, but we have that suitability component that could be added in after more discussions with managers on how it would be useful. I think it's important to consider creating multi-state networks. Imagine a network of Great Lakes states and boats moving between states. I think that would be really powerful with invasive species that are on the doorstep. Like here in Minnesota, we don't have quagga mussels, but of course concerned about it. I'd be very curious about how boats come in, the frequency of it from Michigan or from Great Lakes waters. Additional high-risk pathway networks could be built if data becomes available. And I think we've started to play around, and we just got a grant to do more of this, incorporating prevention or interventions into the network at specific sites or at a entire blanket model for the entire state or county level. If we could reduce risk in a strategic way, what would that do to future invasion? How many invasions could be averted because we invest, let's say, $1 million into decontamination at highly connected nodes in the network? So we could play around with that mathematically and not have to do it in real life and see what happens. So again, there's the website for this dashboard. There's my contact information. If anybody's got follow-up questions, I'd be happy to share more of the detailed methods with people if they've got questions later too.
Thanks, Nick. So that concludes our presentations for today, and we will move on to answering questions and responding to any comments that folks may have. As a reminder, please use the chat box to submit your question or comment. All right, so we will start. I think, Nick, there's a quick follow-up question to confirm that dashboard is available to the public, or is that something that's only available to managers, or like credentials are needed to sign in?
Yeah, that dashboard is available to the public. You can go to that website right now and you should be able to access it. It went live about a week ago. So I'm really happy it happened before this presentation. So it wasn't a TBD slide, but yeah, it's out there and ready for people to use.
Great, thanks. All right, a question for Jeremy, Sandra, and Mark. How many input fields are required for Armor to make a decision to recommend boat wash or decontamination out at a boat launch, for example? Is it just launch site, direction, and boat in the water in the past 2 weeks, or does it need additional fields or variables?
So the answer is currently there's 17 variables in the model. If you go back to the slide that I had with the relative importance, that shows every variable that's present in the model.
So do all of those variables need to be filled in to make a decision, or are there certain ones that are sufficient on their own?
Well, it's just going to get worse if you remove any of them. So I guess that's the answer, is 17 currently, but the fewer the fewer variables that you can provide, the quality of the model will reduce. And that variable importance graph effectively is saying what happens when you remove each of these individually.
Mm-hmm. Thank you. And as a reminder to attendees, we will have a copy of these slides available at the conclusion of this webinar, so folks will be able to go back and reference that slide that Jeremy just mentioned. And we have another follow-up question about the armored decision-making model. In a decision to not wash certain boats that results in cost savings, would you still need staff and equipment? Someone would have to determine the boater's risk and be available to decontaminate, correct?
Yeah, this is Mark. Yeah, that is correct. So the idea is that the boater would come there, the survey would happen, the model would be running on their tablet, and there'll be a decision whether you go. It's like a TSA line, whether you should just go through or go to be inspected and then perhaps washed.
Part of the idea too is to really ring the alarm when it says wash this boat. Hopefully that will kind of wake up the boat wash station attendees and say, this is a boat I should really focus on as well.
And I think along with that, there is a question about, in that sort of TSA line analogy, so waving people through would save money on gas and maintenance fees, but there is a question about how that would add up to the 30 to 60% mentioned in your presentation.
Well, I think those percentages we gave would be how many boats would have to go, through the inspection process. I don't think we've done an economic analysis about how many dollars that would save, but that's an excellent idea. It should be done.
Great, thank you. Let's see, so we have a question, I think, to all presenters, reading straight from the chat now. Boat trailers would also present a risk. Water flows inside the frame during entry and exit from a lake, possibly carrying smaller plant fragments, seeds, villagers, snails, etc. How can this risk be mitigated? I think in the framework of these models, looking specifically at boats, does that include boat trailers or is that a separate consideration?
So that's certainly a limitation of the modeling efforts that we're currently engaged in. Is we can only model the data we have. Certainly, if you wanted to get into the microscopic invasives, then you would have to wash every single boat. But this is, from what we can actually see, I believe, is the data that's provided.
Also, I think usually we consider, Jeremy, correct me, and John, correct me if I'm wrong, and Kathy, but trailers are considered part of the boat. That's part of what's inspected.
That's correct, yes.
Yeah. So trailers do get inspected, but Jeremy's point is a good one. Of course, we're not looking for villagers and small, really, really small things that usually don't get picked up during those inspections.
That should be included in the drain part. So any water containing compartments need to be drained before launching, and also in some cases upon retrieval.
Nick, is trailers included in the Minnesota model?
Yeah, trailers are included as part of the boat. So yeah, it's one of the reasons we did not segment the boats with this first version of the model. We didn't, different types of boats create different types of risk. But even the smaller boats that don't, the boat itself isn't a big risk factor. The trailer that's moving is. So we kept all of that, all of those different boat types, trying to account for the trailers as part of the problem.
And for folks monitoring the chat, Adam Dole has included a clarifier for Minnesota that, like New York, trailers are inspected as part of the watercraft inspection process. While we wait for any more questions to come in, I'd like to offer the floor to our presenters. If you have any other, comments or follow-up statements or questions for each other, feel free to do so.
This is Kathy. I'm not sure if Nick has the answer to this question, but maybe you could direct me to someone who does. How difficult has it been to get the information of where the boat is going to next upon retrieval at the launch? Because we've had a lot of resistance to that question.
Yeah, so in our data set, so there's a couple of problems. One, people don't sometimes know where they're going next. So that removes a fair number of that connection in the network. I don't know, maybe Adam Dahl is in here. He's Minnesota DNR's person who manages the watercraft inspection program, might have more to add, but there are still a lot of people who at least said where they planned to go.
Yeah,
So
thanks, Nick. I can add a little bit. So I'm Adam Dahl. I coordinate Minnesota's inspection program. In general, we get a good number of responses on that. The biggest challenges are, one, the inspector asking the question. Sometimes they just might not ask it, even though it's part of our process. Two, the boater could just always lie or say this same lake. And then there is always that option where, since it's not a requirement, it's always optional. The boater can refuse to give us that info. And then, like Nick said, just due to the sheer number of water bodies that we have here and our lack of originality on names, the lake and county is separate in our survey, because otherwise the list would be massive. And that's a way for there to be errors just from the inspector entering it incorrect, or the boater not knowing what county a particular lake is in. In general, I think most boaters are open to it, especially if the inspector knows enough to explain what it's used for.
Okay, thank you.
Thanks, Adam. Another question for all of our presenters. It looks like in each of the models, Eurasian water milfoil and curly leaf pondweed were included in the modeling. Most of the time, those propagules are big enough to be easily visible, and typically AIS that are easily visually detected have a similar removal efficacy if they are removed by hand versus using a decontamination unit. Can you elaborate on why you decided to include these macrophytes in your model?
Well, this is Mark. I could just start the conversation by saying our approach was to not exclude anything. We wanted to keep all of those, at least for armor, everything involved.
I'll just add to that we're because we're not excluding anything, then we have now a column of, well, if there's a macrophyte on board, maybe there's other invasive species as well. That might be useful to help predict whether or not there's an invasive species on board.
yeah, I would echo it's the same rationale we used. We talked to managers about what some of the concerning species are. We know that those plants can move through the boulder pathway. We did not, in our model, look at the intervention steps. So it was just what could move. Intervention was a separate thing for future work. And we did not include curly leaf pondweed in our model, but we did have Eurasian water milfoil for the watercraft inspection piece.
Thank you. We don't have any other questions from attendees at this point, so once again, I'll give our presenters an opportunity to make any other statements or questions they might have as we give folks one more opportunity to submit any other follow-up questions before we conclude our webinar.
This is Mark for sure again. I would just say that we're really looking for collaborators, and I think Nick's suggestion of really, going beyond the state boundaries. This is not a, they don't stop. Invasive species don't stop at state lines. So broader collaborations are really important and effective for these kind of approaches. And since a lot of this is data-based, that's relatively easily shared.
Thanks, Mark.
Sure.
All right. I will call it there then. Thank you to all of our participants in the webinar today. As has been mentioned several times, if anyone has any follow-up questions for our presenters, particularly after we get this recording and slides shared on the Invasive Mussel Collaborative website, feel free to follow up with them directly with any of your questions. As a reminder, that recording will be posted to the website in the next few days. And if you have any other questions or comments, feel free to also contact us at the Great Lakes Commission. So thank you all and enjoy the rest of your day.
Thanks, Esty.